Hi, I'm Dr. Mark Paradis, and this is a lecture on probability and statistics. Throughout the lecture, we'll have multiple different exercises that you can complete. I encourage you to complete them during the slideshow. Just press pause, complete it, and resume the video once you think that you have your solution. All right, so probability is something that is really important in our everyday lives, but it's also something that most people don't really have a very strong understanding of. And it can have impacts on your real life, including participation in things like game shows, which I know in our everyday life may not seem very important, but this is just an interesting example of how misunderstanding probability can lead to bad outcomes or not outcomes that we'd want. So let's take a look at an old game show called Let's Make a Deal. We're going to start with kind of just putting it a mise-en-scène, and then at the end, we'll look at what is the solution, right? So picture a game show where there are three different doors, so door 1, door 2, and door number 3. Behind one of the doors is located a brand new car, and behind 2 of the other doors are located goats. So while you might like winning a goat, most people would probably prefer that they would like to win a car. So which door do you choose, and does it matter? So in terms of does it matter, let's just assume that the car is randomly placed behind one of the 3 doors. In that case, it doesn't really matter whether you choose door 1, door 2, or door number 3 from a statistical standpoint. There's no way of knowing beforehand which is the right answer. You've got an equal chance in each case. So let's assume that for today's purpose, we choose door number 2. Right, so our host, Monty Hall, after we've chosen door number 2, he opens door number 1 to show us that there's a goat behind door number 1. So now we're left with a kind of, it appears that we've got a 50-50 chance, if you ask most people, right? We've got our door that we've picked, door number 2, and we've got then door number 3, which we haven't seen what's behind. And so Monty Hall asks us whether we'd like to stick with door number 2 or whether we would like to switch to door number 3. And the question becomes, do you stick with your original pick of door number 2, or do you switch to door number 3? And does it matter? And we're going to return to this near the end of the lecture as to whether it matters whether you choose to switch or whether you choose to stick. All right, so let's start with the basics of probability, right? And when we start with the basics of probability, often we end up dealing with a coin or tossing more than one coin because it's a relatively simple example that most people can easily grasp. So we're going to be repeatedly talking about flipping coins throughout today's lecture. So let's start with 2 possible coins. And the figure below shows kind of everything that could happen if you flip 2 coins, right? So there's 4 possible what we would call outcomes, right? You can land on heads, 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 tails, tails, heads, or tails, tails, right? And so each of these 4 different ways that the 2 coins can fall, we would refer to as an outcome, right? But if we look at kind of properties that we might be interested in terms of, let's say, how many heads there are from flipping 2 coins, we'd see that there's 3 possible, what we would refer to as events, right? So we could get 0 heads, we can get 2 different instances of 1 head, and we can get we can get 1 possible event of 0 heads, sorry, or of 2 heads, right over here. And so we would say that there are 4 possible outcomes, these 4, right? But they represent 3 possible events of some property of interest, right? So if we're not interested in the number of heads, there's 3 possible events. Same thing if we're interested in the number of tails, there'd be 3 possible events, because these 2 different outcomes, right, are the same in terms of the property of interest. So we define outcomes as the most basic possible results of an observation or an experiment. So heads, 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 tails, tail, head, and tail, tail. An event is a collection of 1 or more outcomes that share a property of interest. So the number of coins that land on heads or the number of coins that land on tails. And so we're going to talk a lot about outcomes and events throughout today's lecture. So before we go any further, it's important to understand kind of how we can write or express probabilities, what is kind of the notation that we're going to be using, and a little bit just about kind of what are the limits of probabilities, what values can probabilities take on. So if we want to talk about the probability of the event, we write it in terms of P, that event. So a probability of one head, we'd write one head here, or probability of two heads, we'd write two heads here, two tails. And probabilities always must be located between 0 and 1 inclusively, right? So if we have probability event is equal to 0, then that event is impossible, right? We can't go lower than 0 because something can't be less than impossible. If the probability event is equal to 1, then the event is certain, right? But we can't go above 1 because something can't be more than certain. We can't have something that occurs more than 100% of the time. And then we're frequently going to see in many of the examples, particularly flipping coins, probability of event is equal to 0.5, right? So this means there's a 50% chance that the event will occur. So flipping a single coin, you've got a 50% chance that it lands on heads, a 50% chance that it lands on tails, if we assume that the coin is fair. So how can we find the probability of something, right? And so there's three different approaches that we can use. So we can use the theoretical probability, we can use relative frequency probability, and we can use subjective probability. And so we're going to look at each of these in turn. So theoretical probability assumes that all events are equally likely, right? And so if we can assume that all events are equally likely, so flipping a fair coin or rolling a fair dice, right, then we can use kind of a set of rules based on our theoretical understanding of this process, right? So step one is count the total number of possible outcomes. And we're going to continue with our two coins, right? So when tossing two coins, there's four possible outcomes: head, head, tail, tail, head, and tail, tail. Step number two, among all the possible outcomes, count the number of ways the event of interest A can occur. So event of interest A might be the number of times it lands on heads. So when tossing two coins, there are two events that include an outcome of one coin landing on heads. So when we get head tail and when we get tail head. And then step three, determine the probability of event A from using this following formula. So probability of event A is equal to the number of ways that A can occur divided by the total number of outcomes, right? So the number of events divided by the number of outcomes, right? So if we're looking at probability one heads, or if the two coins of landing just one head, we have two possible events, right, where we land on, where we get one heads, and we have four possible outcomes. The 2 divided by 4 is a probability of 0.5. So we would say that the probability of getting one heads when flipping two coins is equal to 0.5. So let's try an example, right? So suppose that you select a person at random from a large group at a conference. What is the probability that a person has a birthday in July? Now assume 365 days in the year. Just because if we put in the leap year, that adds an extra complexity that we don't really need. So pause the video, try calculating this, and once you think you've got a solution, resume the video and we'll take a look. All right, now that you've found your solution, let's take a look. So if we assume that all birthdays are equally likely, right, which we would need to do to be able to use this theoretical method, we can use a three-step theoretical method. So step one, each possible birthday represents an outcome. So there are 365 possible outcomes. Step two, July has 31 days, so 31 of the 365 possible outcomes represent the event of a July birthday. So we have 31 different events. And then step three, probability of a July birthday is equal to 31 divided by 365, which is about equal to 8.5%, so a probability of about 0.08, which is slightly larger than a 1 in 12 chance which makes sense given that July is just 1 month, and slightly more because some months have 31 days, some months have 30 days. Those with 31 days should have a slightly higher probability than those that have 30 days. And then we have February too, which would have the lowest probability of all of the different months. All right, so far we've looked at a relatively easy case of flipping coins where it's easy to see how many outcomes there are, say, flipping 1 or 2 coins. But sometimes we run into situations where the process is more difficult, right? It's harder to figure out just looking at how many different outcomes there are, particularly when we're dealing with multiple different flipping many coins or things that have more than 2 different options. And so we need kind of a rule for figure out how many possible outcomes there are. And so it turns out that there's actually a relatively simple method for doing so, right? So let's again start with our 2-coin example. Suppose we toss 2 coins and want to count the total number of outcomes. The toss of the first coin has 2 possible outcomes, heads and tails. The toss of the second coin also has 2 possible outcomes. The 2 outcomes for the first coin can occur with either of the 2 outcomes for the second coin, right? And so we can see this here. Coin number 1, whether we get heads or tails, right? Coin number 2 also has a chance of getting heads or tails. So if we flip heads on coin number 1, we can also get heads or tails on coin number 2. And if we flip tails on coin number 1, we can also get heads or tails on coin number 2. And so this leads to our 4 possible outcomes. And we can extend this thinking. For example, if we toss 3 coins, we have a 2 by 2 by 2, so 8 possible outcomes. And you can draw it out and see that this is the case. So we have head, 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 tail, and you can read through all the different possible outcomes. And here it is drawn out below. So whatever we get on coin number 1, right, we can get a heads or tails on coin number 2. And whatever we get on coin number 2, we can get heads or tails on coin number 3. And so we there have all of the different possible 8 outcomes. All right, so more theoretically, we want to kind of turn this, what we just saw, into something generalizable that we can use in many different cases. So suppose that process A has A possible outcomes and process B has B possible outcomes. So process A might be flipping coin number 1, and there's so A possible outcomes, 2 possible outcomes, and process B is flipping coin number 2, and so there's B possible outcomes. Assuming the outcomes of the processes do not affect each other, the number of different outcomes for the 2 processes combined is A times B. So 2 times 2 is equal to 4 in the case of flipping 2 coins. This idea extends to any number of processes. When we say that the outcomes of the processes do not affect each other, right? We're talking about, say, again, in flipping coins, flipping coin number 1 doesn't impact the results of flipping coin number 2, right? Whether coin number 1 lands on coin number 2, or sorry, whether coin number 1 lands on heads or whether it lands on tails has no impact on the result for coin number 2. And we would have to do different calculations in the case where the 2 processes do affect each other. So if we add a third process, say flipping a third coin, and process C has C possible outcomes, the number of possible outcomes for the 3 processes is A times B times C. So the number of possible outcomes for A times the number of outcomes for B times the number of outcomes for C. All right, so how many outcomes are there if you roll a fair die and toss a fair coin? So give this a shot, pause the video, and resume once you think that you've got your solution. All right, now that you found your solution, let's take a look at the correct answer. All right, so the first process, rolling a fair die, has 6 outcomes, right? So dice you can roll through 1 through 6. The second process, tossing a fair coin, has 2 outcomes, heads and tails. Therefore, there are 6 times 2, so 12 outcomes for the 2 processes together, right? You could get a 1 with the heads, you can roll a 1 and flip the tails, you can roll a 2 and flip the heads, you can roll a 2 and flip the tails, so on and so forth. I'm not going to list all of them out loud. So this rule allows us an easy way, so you don't have to just normally write out all the possible outcomes, as long as you know that there's 6 outcomes for rolling a die, or rolling dice, and that there's 2 outcomes for rolling, or for flipping a coin, then you could easily calculate that there's 12 possible outcomes for the 2 processes together. So here's another example, and so give it a shot. So what is the probability of rolling 2 ones, snake eyes, when 2 fair dice are rolled? And we say fair dice because dice that are loaded or unfair, where you have we can't use the theoretical method because not all outcomes are equally likely. So it's important that they are fair dice or fair coins. All right, so give this a shot, pause the video, and once you've got your solution, resume, and we'll look at the solution together. All right, now that you've got your solution, let's take a look at it together. Rolling a fair die has 6 equally likely outcomes. Therefore, when 2 fair dice are rolled, there are 6 times 6, so 36 different outcomes. Right? But that we didn't just want to find the number of outcomes, we want to find the probability of rolling 2 ones. So of these 36 outcomes, only 1 is the event of interest, snake eyes. Right? There's only one way of getting 2 ones. So the probability of rolling 2 ones is 1 divided by 36, and that's about equal to almost 3% chance, probability of 0.278. So far we've been using the theoretical method, and the theoretical method is really easy. And if you know the rules, right, if you know that each different outcome has equal likelihood, it's a very simple method to use, right? But we don't always know whether an event has equal likelihood of happening or an outcome has equal likelihood of happening. Sometimes we don't know the rule behind it, and sometimes we just absolutely know that there's not equal likelihood of different outcomes happening, right? And in those cases, we can't use the theoretical method. So the relative frequency method is something that we can use instead in those cases. So the second way to determine probabilities is to approximate the probability in event A by making many observations and counting the number of times event A occurs. And so we call this the relative frequency or empirical method, right? So if we can count enough, if we can observe enough different instances of a particular event or a particular process, then we can get an idea of how likely that event is for that process. So there's a lot of debate as to how many different processes you need to see, how many different events, how many different outcomes you need to see before you can come up with a conclusion. More is always better. So how does this method work? So step 1, again, we've got a multiple step process. Repeat or observe a process many times and count the number of times the event of interest A occurs. So how many times that we roll 2 ones, or we roll a 3, or sorry, we flip 2 heads, or 1 head, we roll a 3 when rolling dice. Second, estimate the probability of A by taking the number of times A occurred and divide by the total number of observations. So for example, if we want to calculate the mortality rate of a disease, we cannot use a theoretical method. It wouldn't work in this particular case because we don't know the rule behind it, and we can't say that there's an equal likelihood occurring. So we would need to calculate the number of deaths from a disease and the total number of infected, right? So we would divide the total number of people who died from the disease by the total number of people who were infected by that disease, and then we'd be able to see the probability of death from being infected by that disease. The third way of assessing probabilities is subjective probabilities, and this one is one that we probably use a lot intuitively, or when we're not calculating something. It's also probably usually the least accurate because we're relying on our experience or our intuition. If you're an expert on a certain subject, your experience or intuition may lead to a good approximation of the probability. But oftentimes, if you're not an expert in a certain area, it can lead to a lot of incorrect assessments. And we see this a lot in how people make decisions, and particularly in areas of gambling where people follow a lot of flawed logic. All right, so to conclude on the 3 approaches to finding probability, we have theoretical probability is based on assuming that all outcomes are equally likely, determined by dividing the number of ways an event can occur by the total number of possible outcomes. The second is the relative frequency or empirical method, and it's based on observations or experiments, the relative frequency of the event of interest. And the third approach is the subjective probability. It's an estimate based on experience or intuition. So just based on our gut, based on what we've seen in our lives. All right, so far we've talked about the probability of an event occurring. Sometimes we want to know how likely is it that something won't occur. So if the probability of event A is the probability of A, right? So we're the probability of A, and the probability that event A does not occur is the probability of not A. And so that's one way that we could write it. And there's, particularly if there's, only, or we know some things quite clearly about probability not A. And because something must occur or not occur, right? We can write that the probability of A plus the probability of not A is equal to 1, right? So if we flip a coin, right, and we want to know the probability of it landing on heads or probability of it not landing on heads, right? It can only land on heads or not land on heads. There's no other possibility, right? So it must sum to 1. Or if we want to know, probability of rolling a 1 and the probability of not rolling a 1, right? Well, you either just logically have to roll a 1 or not be 1. There's no other, you can't half roll a 1. And we can rewrite it another way. Probability not A is equal to 1 minus probability of A. So we've just rearranged this, this is the more useful formulation if you're interested in the probability of an event not happening, right? So if you know the probability of the event happening, then you just take 1 minus the probability of it happening, and you end up with the probability of it not happening. We refer to the probability of event not happening as the complement of the event, and the event, the not is often replaced by a bar, right? So if you see a bar, that means not A. So a probability distribution represents the probabilities of all possible events, right? Because often when we're looking at a different process, we want to see how likely are different events, with likelihood of different events happening, right? So suppose you have tossed 2 coins simultaneously. The outcomes are the various combinations of a head and a tail on the 2 coins. Because each coin can land in 2 possible ways, heads or tails. We've talked about this a lot so far today. The 2 coins can land in a 2x2 4 different ways, right? So coin number 1, coin number 2, all the different outcomes and the probability of each. Because in the case of a coin, we know that each outcome has equal probability. So it's easy to fill in that each one of these has a 1 in 4 chance or 25% chance of occurring. So the 4 outcomes represent only 3 different events: 2 heads, 2 tails, and 1 head and 1 tail. So the probability of 2 heads is equal to 1 in 4, or 0.25. The probability of 2 tails is 1 in 4, or 0.25. And the probability of 1 head and 1 tail, so probability head and tail is equal to 2 and 4. 2 different events, 4 possible outcomes is equal to 0.5. And so we can put the distribution into a table or a histogram. It makes it easier for people to see and for people to understand what is the distribution of probability of each of the different events, right? So here we've got 2 heads, 0 tails, 1 head, 1 tail, 0 heads, 2 tails. We've got the different probabilities, and helpfully they have to sum to 1, right? So that makes it easy to check whether you've done it properly. And in this case, we've got a histogram, right? So number of heads, 0. There's a 0.25 probability, 1, there's a 0.5 probability, and 2, there's a 0.25 probability, right? So we get a lot of information just from looking at this table about how likely different events, this graph, just by about the probability of different events, just from looking at it. So it conveys a lot of information quite easily. So how do we make a probability distribution, right? How do we get to that table or to that graph, right? So we have a series of steps to follow. So step 1, list all possible outcomes. And you can use a table or a figure if it's helpful to figure out how many possible outcomes there are. Identify outcomes that represent the same event. Find the probability of each of these different events. And then step 3, make a table in which one column lists each event and another column lists each probability. The sum of all probabilities must be 1. If it's not sum to 1, you've missed something, right? So if we go back to the last slide quickly, right, we've got one column with all of the different possible events, and then one column with all the different probabilities, and we see that they sum to 1. All right, so let's give this a try. So make a probability distribution for the number of heads that occurs when 3 coins are tossed simultaneously. And so give it a try, pause the video. You have access to the slide. So if you need to check those 3 steps again, you can go to the slides and help figure out how we can make probability distribution with 3 coins are tossed, and resume the video once you've got your probability distribution. All right, so we can use the 3-step process to accomplish or to create the probability distribution. So step 1, the number of different outcomes when 3 coins, sorry, not cons, are tossed is 2 by 2 by 2, so 8, because each coin has 2 possible outcomes, and all 8 possible outcomes are listed here. Step 2, we need to find all the different possible events, right? So there are possible events of 0 heads, 1 head, 2 heads, or 3 heads. So tossing 3 coins, those are all the possible events that we can get. So probability of 0 heads is 1 in 8. So if we, sort of tail. Probability of 3 heads is again 1 in 8, head. And then the probability of 1 head and of 2 heads is 3 out of 8. So now we've got the probability of all the different events. And we can now make a table with 4 events, the 4 events listed in the left column and the probabilities in the right column. You could also make a histogram if you'd like. That we'll put the probabilities on the y-axis and the different events along the x-axis that we saw before. And in this case, it sums to 1, right? 1 8 plus 3 8 plus 3 8 plus 1 8 is equal to 8 8 or just 1. All right, so now we're going to talk a little bit about the law of large numbers, or the law of averages. And this applies to a process for which the probability event A, probability of A, and the results of repeated trials do not depend on results of earlier trials. And we call this, they are independent, right? So again, flipping coins, flipping the first coin, the result of flipping the first coin doesn't affect the result of flipping the second coin. And it states that it's a process repeated through many trials. The proportion of trials in which event A occurs will be close to the probability PA. The larger the number of trials, the closer the proportion should be to PA, right? So think about flipping a coin, right? And the probability of, say, landing on a head for flipping a coin, so probability of A, is equal to 0.5. But if you, say, flip only a coin once, you can't possibly end up at 0.5, right? It either lands on a head, so 1, or it lands on tails, so the proportion is 0. The more times you flip the coin and you take the proportion of times that it lands on heads, or the proportion, you'll see that as you go through more trials, the proportion gets closer and closer to the true probability of A, right? So if you flip it 10 times, it depends on how lucky you got those 10 times. If you flip it 50 times, you're probably getting a little bit closer to the probability of A. If you flip it 100 times, 1,000 times, 50,000 times, the more times you do it, the closer the proportion will get to probability of A, right? So you might sometimes, particularly in short run spans, go through anomalous runs, right? You might flip, 3 or 4 straight heads, right? But across 50,000, you're not going to go through an anomalous run of 50,000 usually. So the more times that you do it, the more that it should get closer to the true probability of A, the proportion that you get from multiple different trials. And so this is important in understanding the concept of expected value. So the expected value of a variable is the weighted average of all its possible outcomes. because it's an average, we should expect to find the expected value only when there's a large number of events. So the law of large numbers comes into play, right? So think about basketball players, right? Each different player has different likelihood that they're going to score, right? Better players, are more accurate shooters often, and so they're going to score more on a higher percentage of their shots. And then worse players, or if I were playing, the likelihood that I'd score a basket would probably be quite low, particularly compared to professional players. But if we look at a single trial, the ball's either going to go in the net or it's not going to go in the net. And so, we're not going to see, say that a player scores on 80% of their shots, right? It's either in or it's not in. But if we, and if you see 5 shots, maybe, they're doing really well that game and they got 5 straight in a row, even if they're, a mediocre shooter. And, sometimes even the best shooter, sometimes LeBron James will miss, 3, 4, 5 shots in a row. And that's going to happen, right? But if you look across an entire season, and you're even going to see if you look at games, right? Like even the best player is going to have, bad games, and even, the worst players in the NBA will have, really good games. So you'll see games where a player's, average will deviate, a lot from, what we would expect from the probability from the shooting average. But if we look across a season, right, then you're going to start seeing that, their average is going to get really close to their to the probability of them scoring, the true probability of them scoring. So the expected value is the weighted average of all possible outcomes, right? And so we can say that, if we're looking at the outcomes of score or not score, the expected value is the weighted average of, do we expect them to score or not? So, there's a 0.8 chance that they're going to score, or there's a 0.75 probability that they're going to score, or a 0.5 probability that they're going to score. And so how do we calculate this, right? So let's consider 2 events. So you could think of it of, scoring or not scoring, right? And there's a value and a probability for each. So let's say scoring, I know in basketball you get 2 or 3 points, but let's just say value event A is 1 for scoring. So think of free throws then. And probability event 1, so you've got a value scoring of 1 for scoring, and a probability of it occurring, say a decent shooter, so, 0.9 or 0.85% chance of this to score the free throw, right? And then there's value event 2, so not scoring, so 0 points, times the probability of event 2. So if they've got a 0.85 chance of scoring, and they have to score or not score, then there's a 0.15 chance of them not scoring. And so if we want to see the expected value for them shooting, right? So on average, what do we expect to happen? We can, calculate it using this formula. And in that case, there'd be a 0.85, right? The expected value would be 0.85. It's 1 times 0.85 plus 0 times 0.15 times to 0.85. So the expected value for that player taking a free throw would be 0.85. So we could say that, there's a high probability that we expect them to score on any individual shot, but we also have to remember that with any individual shot, anything can happen, right? There's still that 15% chance that they miss. So the expected value really is expected to operate, across, a season, maybe a half season, a game, a month. And this formula can be extended to any number of events by including more terms in the sum. So more formally, we can write this as the expected value of x, so is equal to the sum of value event x times the probability of event x, right? So we take, event 1 times the probability of event 1 plus event 2 times the probability of event 2 plus event 3 times the probability of event 3, going through all the, the different events. And once we've done that, we get the expected value of x, so scoring, not scoring, or whatever it'd be with 3. So that's just a notation. So this is just a summation of all the different possible, outcomes. So or events. Now, if you're paying careful attention to the formula that we just saw for expected value, so expected value of x is equal to the sum of x times probability of event x. So you may recognize it from a previous lecture, right? And so it's so fundamental that it's also given the name, the population mean or sample mean, right? So when you learned about the relative frequency way of calculating either the population mean or the sample mean, right? This was the formula that we saw. So the expected value really is just, it's the same as the mean, right? So on average, how often do we expect that the person will score a basket or score a free throw? So when we're talking expected value, we're really talking the mean. All right, so far we've been kind of, looking at one probability, but sometimes we want to combine different probabilities and calculate, how likely is something to happen. And so let's start with what we call AND probabilities for independent events. And we'll talk about with both AND probabilities and independent events. Let's start with independent events because we've already touched on it before. So again, let's use the example of flipping 2 coins. Flipping 1 coin doesn't impact what happens to the other coin. The other coin in no way is influenced by what happened with that first coin. So in general, we call the probability of, so now the AND probabilities. So in general, we call probability event A and event B occurring an AND probability. You could also refer to it as a joint probability, right? So say you flip 2 different coins, the probability that you get a head for the first coin and you flip a second coin, the probability that you get a head on the second coin. The probability of head on the first, probability of head on the second, right? So this actually looks a lot, quite similar to what we were seeing before. So consider 2 independent events, A and B, probability A and probability B. The probability that A and B occur together is probability A and B equal to probability of A times probability of B, right? So probability of getting, so probability of say heads on coin 1 and heads on coin 2, probability of getting heads on coin 1, so 0.5, times probability of getting heads on coin 2, so 0.5. And so then 0.5 times 0.5 would be your probability of A and B. And this principle can be extended to any number of independent events, right? So probability of A and B and C would be probability of event A times probability of event B times probability of event C. This can go on for as many different events as you'd like, as long as they're all independent. Because this logic is really similar to what we've seen before with calculating probabilities, won't do an example, but we'll do an example for this next one, probability for dependent events, right? So far we've been dealing with independent events, so flipping multiple coins, but they don't influence each other, right? But 2 events can be dependent if the outcome of one event affects the probability of another event, right? So let's think about if you've got a bowl of Smarties or M&Ms, right? And you want to see the probability that you get, a red one on the first and your second pick, right? So if you take one out of the bowl, right, and you see whether it's red or not, right? And you don't put it back in, and then you reach into the bowl and take out a second one, right? The probability of getting red on the second one isn't the same as it was on the first one, right? Because after you've taken that first candy out of the bowl, you now have 1 fewer candy in the bowl, right? So say there's 100 for the first one, you now have 99 candies left when you're taking out the second one. So it's not the same probability. And depending whether you got a red on the first one, there's now also a different number of reds in the bowl potentially. So when we're dealing with events that influence each other, then we have to take that into account. Now, do note that if you would put that first candy back into the bowl, right, and you shook it up so that, it was everything, got mixed back together, then we'd say it's independent, right? Because you put it back in, you shook it up. So, what you took on the first one doesn't influence what you took on the second one. So it's only when we don't have what we call replacement that this would be a dependent event. So in this case, we look at probability event A and B. So say getting 2 red M&Ms, probability of getting red on the first one and getting a red on the second one is equal to probability of event A times the probability of event B given that event A occurred, right? So we would say this notation, right, the way we would say that we would correctly say it or think about it is probability of D given the occurrence of event A. And we refer to this as conditional probability, so conditional on A having occurred. And like before, we can extend this logic to any number of individual events, right? So probability of A and B and C be probability of A times probability of B given A and probability of, C given B. So let's give an example because this is a little bit different from the things we've talked about. So let's give, a try so that hopefully through a little bit of practice or through an example, this will help become a little bit more concrete. So think of 15 memory cards. And in this deck of 15 memory cards, there's 5 defective cards. And so we want to know what's the probability of getting a defective card on the first, second, and third selection, right? So you select 3 different cards out of the deck of 15 cards. We want to know the probability of getting a defective card on each of the 3 different picks. So pause the video, give it a try. And once you think you've got the solution, resume and we'll see if you got the right answer. All right, so here's the solution. So probability of getting 3 defective cards is equal to the probability of getting a defective card on the first one times the probability of getting a defective card on the second one, given that card number 1 was defective, times the probability of getting a defective card on the third pick, given that card number 1 and card number 2 were defective. And so this is how it works. So probability of getting a defective card on the first pick is 5 over 15, right? Because there's 5 defective cards and there's 15 outcomes, right? So the 15 outcomes, 5 different events, right? But it's not the case that we have to take into account what happened on the first card when looking at the second and third ones, right? So we've now, when we look at the probability of getting a defective card on the second pick, right, we're dealing with, there's now 1 card that's out of the deck, right? So there's only 14 cards left. And we've said that we've taken a defective card out on the first one. So there's only 4 defective cards left. So for the probability of getting a defective card on the second pick is 4 out of the 14, right? And then when we're dealing with the third card, we know that 2 cards have already been removed, right? So there's no longer a deck of 15 cards that we're choosing from. We're choosing from a deck of 13. And there's no longer 5 defective cards left. There's 3 defective cards because we've already taken 2 out. So the probability of getting a defective card for card 3 is 3 divided by 13. And if we multiply these together, we get a probability of 0.02, so about a 2% chance of getting these. All right, so dealing with dependent events, as you could see from this example, is rather annoying, and particularly if you're dealing with multiple possible events, right? And A through 100 different ones. Doing that for each of them would be quite annoying. So in general, as kind of a rule of thumb, if relatively few items or people are selected from a large pool, then dependent events can be treated as independent events with very little error. So a common guideline is that independence can be assumed when the sample size is less than 5% of the population size. This practice is commonly used in polling organizations, right? So if we're taking a poll of 1,000 Canadians out of, about 37 million, technically once you've selected one, because you can't hit that person again, that second person you've chosen isn't independent, right? So it's dependent on, so the probability of that person being female depends on whether the first person was female or male, right? Because you've removed one from the pool, you can't take the same person twice. But given that the sample is such a tiny proportion of the population, right? We typically just treat it as if each one was independent, right? And there's no real, in this case, big loss of accuracy. So when we're dealing with a sample that's less than 5% of the population, it's acceptable to treat dependent events as if they're independent, just because it makes your life just a lot easier. All right, so far we've been talking about and probability. So when, probability event A and event B occurring, so we get, a head and a head, so a head on the first one and a head on the second one, right? But sometimes we'd like to know the probability of getting, rolling a 1 or rolling a 2 on a dice. And so there's two possible ways that can go. So two events that can be non-overlapping, right? So we can do either or probability when event. So non-overlapping, and then we'll look at overlapping after. So two events are non-overlapping if they cannot occur at the same time, right? So if A and B are non-overlapping events, the probability that either A or B occurs is probability of A or B is probability of A plus the probability of B. And this can be extended to any number of non-overlapping events, right? So if you think about flipping a coin, right, it lands on heads or it lands on tails, right? And these aren't overlapping. It can't land somewhere in between the, it's on heads or tails. It's not partially on one or the other. And so if we want to find the probability, and this is easy when we're dealing with, kind of two, like the head or tail example here, right? You get the probability of it landing on heads is, 0.5 plus the probability of landing on tails is 0.5, and probability of A or B then becomes 1, 0.5 plus 0.5, and that makes a lot of sense, right? The probability of a coin landing on heads or tails, and that's all possible, outcomes that we can get. So obviously it would be a probability of 1. So let's try an example. Suppose you roll a single die. What's the probability of getting an even number? Right, so pause the video, give it a try, and once you think you've done a solution, resume, and we'll take a look at what the correct answer is. All right, now that you've found your solution, let's take a look. So even outcomes are, rolling a 2, 4, or 6, and these are non-overlapping because a single die can yield only one result, right? You can get a 2, 4, 6, 1, 3, 5, right? So a single die can't give more than one of those at one different time. And we know that the probability of getting a 2 is 1 in 6. Probability of rolling a 4 is 1 in 6. And the probability of rolling a 6 is 1 in 6. And therefore, the combined probability of getting 2 or 4 or 6, or rolling an even number, is 1/6 plus 1/6 plus 1/6, which is equal to 1/2. So probability of 0.5. Now, two events, so just like how dependent ones made our lives a little bit more complicated compared to independent events, when two events are overlapping, it makes our life a little bit more complicated compared to non-overlapping. So two events are overlapping or non-mutually exclusive events if they can occur together. The probability that either A or B occurs, probability of A or B is equal to probability of A plus probability of B minus the probability of A and B together. And the last term, probability of A and B, corrects for the double counting of events in which A and B both occur together, right? So imagine that we want to say, think about the probability that someone is, a Montreal Canadiens fan or a Montreal Alouettes fan, right? So we would count all the people who are Montreal Canadiens fans, and we'd count all the people who are Montreal Alouettes fans, and this would seem simple, except for the fact that, there's a lot of people who are both fans of Montreal Canadiens and the Montreal Alouettes, right? So think of someone, just randomly named John, right? So if he's a fan of both, so we would count him here, and we'd count him here, right? Because he's both a fan of Montreal Canadiens and a fan of Montreal Alouettes. We would have double counted him, and so we'd have an inaccuracy, or we'd have an inaccurate assessment of the probability of A or B, because we would have counted John twice, and we don't want to be doing that, right? So we have to take that into account by subtracting people who are fans of both, so that we don't double count these people. And we're going to do an example where it'll become clear of how important this can be, and how obviously inaccurate the results can be if you don't take this into account. So to improve tourism between France and the US, the two governments form a committee consisting of 20 people. There's 2 American men, 4 French men, 6 American women, and 8 French women. Now, if you meet one of these people at random, what is the probability that the person will be either a woman or a French person? Right, so pause the video, give it a try, and resume when you think you've got your answer. All right, so here's the solution. All right, so we have 12 of the 20 people are French. Right, so probability of French is equal to 12 on 20. So we got that right here. The probability of meeting a French person is 12 on 20. Similarly, 14 of the 20 people are women. The probability of meeting a woman is 14 on 20 right here. Now, we have to take into account here, though, that 8 of the French, there's 8 French women included in the committee. And so they would be counted in both the women and the French categories, right? So they'd be counted both for the 12 and 20 and 14 and 20, right? And so if we don't correct for this, if we don't correct for the double counting, we'd end up with the kind of like ridiculous situation of calculating 14 on 20 plus 12 on 20, right? So we would end up saying that 26 out of 20 people are either women or French, right? And quite obviously 26 out of 20 people can't be anything because you can't have 26 out of 20 people. So if we take away, if we subtract the 8 French, and of the 8 French women who are included in both groups, if we subtract them out, then we end up with 18 of the 20 people are either women or French. So 0.9, probably 0.9 of running into someone who's a woman or French. So we've pretty much just left out the 2 American men. And so that makes sense, right? Only 2 of the people are not French, nor are neither French nor women, right? So that's the 2 that are missing here, as we get a probability of 0.9. All right, so let's return to our Monty Hall problem. So in case you're really curious about what would happen if you go on the game show, how should you play? Remember, though, that if you go on any game show, there may be statistical rules that can help you. But like we learned with the law of large numbers, in any given instance, right? Statistics may be in your favor based on a certain choice, but in any individual case, any outcome is possible, right? So even if you got 90% chance of something happening, that does mean that 1 in 10 times it won't happen. And if you're unlucky and that 1 in 10 times is your time, even if you choose the statistically correct approach, you may not win, right? So just a kind of reminder of the let's make a deal. So we refer to this let's make a deal thing as the Monty Hall problem. So again, we had 3 doors to choose from, and behind one of them is a car, and behind 2 of them is a goat, right? And so you get to choose which one that you'd like to take. We already said if there's an equal probability, or we can assume that the car is randomly placed behind one of them, so it doesn't really matter which door we initially choose. I mean, it does in terms of whether we win, but statistically, mathematically, there's no correct answer here at this stage because we have no information that can help us, guess which one is right. So our host, Monty Hall, we chose door number 2. Our host, Monty Hall, opens door number 1 and reveals a goat. And then he asks us, do we want to stick with door number 2 or switch to door number 3, right? And we want to know, do we switch, and does it matter? And the answer is that, yes, actually, it really does matter. This is something that most people have trouble understanding, that actually it really, really does matter. So most people will understand that at the beginning, you've got, a 1 in 3 chance that you're going to, guess properly. So, if you guess door number 2, you've got a 1 in 3 chance that the car is here, and 2/3 chance that, it's somewhere else. But once we take away this door, most people then look at it as, okay, there's 2 doors left. There's a 50-50 chance that it's, behind door number 2. There's a 50% chance that it's behind door number 3. And while it's an understandable conclusion, it's ignoring information that we had, right? And so rather than being resigned to the idea of it being a 50-50 chance, we actually have more information that could allow us to make, a better decision. And it turns out that if you switch doors, you actually have a 2/3 chance of being right. So Now, in real life, some people choose to switch and some people choose to stick with their original pick. Most people would say it doesn't really matter. And even once, I explain this to some of you will be very resistant to believing me. And I've explained it to many people before, and just some people refuse to, accept that it's not a 50-50 chance whether you switch or not. Statistics shows us so that you should always switch. And let's look through all the possibilities to see why that's the case. Right, so you choose a door, right? And let's imagine that the car is located behind door number 3, right? So the car is over here. And so here's all the possible outcomes that we can have, right? So you choose door number 1 with a goat, right? Because the car is really behind door number 3. So you choose door number 1, right? And so Monty would open door number 2, right? And then ask you, do you want to switch or stay the same? If you stick, you lose. You switch, you win. Now let's assume that you pick door number 2, right? And so Monty Hall would open door number 1 because it's not going to reveal the car. So he opens door number 1, right? And he asks you, do you want to switch or do you want to stick? If you stick, you lose. If you switch, you'd be switching to door number 3 and you'd win. So the only time where it hurts to switch is if you actually guessed right on the first pick or on your original pick, right? So in that case, if you stick, you win, but if you switch, you lose. And so most people, when one door gets eliminated, say this door gets eliminated, right? They're like, okay, there's a 50% chance between these 2 options. But really, they're ignoring that when you made your initial selection, you had a 1/3 chance that you're right. So you chose door number 2, you've got a 1/3 chance that it's here, and a 2/3 chance that it's somewhere else, out of door number 1 or door number 3, right? And that possibility or that information doesn't stop being true when door number 1 is open. It's still the case that you've got a 1/3 probability that you are right and a 2/3 probability that's in one of these 2 places. Now, given that we know it's not here, that means that there's a 2/3 probability that it's behind door number 3. So it's important to keep that initial information and not discard it when one of the doors is open, right? It's still always the case that your initial pick was only a 1/3 chance that it was right. Yes, initially there was a 1/3 chance that it was behind door number 3 and a 1/3 chance behind door number 1. But we gained additional information, right? So we know 1/3 chance here, 2/3 chance not here. That's still always the case, right? So if you switch, you have a 66% chance of winning. Now, to solve the problem mathematically, you require the use of Bayes' theorem, which is beyond the scope of this class. But it involves the importance of prior information and how we update our beliefs. And so just be careful that you don't discard information that we already had, right, in favor of looking at it as a 50-50. All right, so that concludes today's lecture. So there's practice problems that available on Leia that you can download, and solutions that are there too. So you can try out some of these different concepts and to make sure that you understand things, and definitely get in touch with me if there's anything that is not clear about probability. So I hope you enjoyed this lecture and that you've learned something about probability, and hopefully it'll help you win a car, or it helps in a lot of things beyond just gambling and game shows, but just understanding the likelihood of events occurring around us. It can help you understand every time we're dealing with things like insurance or anything else like that, probability is involved. And so understanding it can make you a better consumer and can help you make better decisions in your life.